All right, we're going to talk about the Pre-Cal 4.5 notes. And the first thing we need to do is we need to note that we're talking about the parent graphs and developing and manipulating those parent graphs to match a graph that we need. So we're talking specifically about manipulating the exponential parent graph. And remember that parent exponential functions have the form p of x is equal to b to the x power. Now you're going to notice this is different than the equation that we looked at in 4.4 where we had an a in front of this. Well, remember, we're talking about the parent graph. We're talking about the base, the simplest version of the graph that there is. The a is going to adjust it, and that's what we're going to talk about, how the a comes in, how an x minus 1 power affects it, and something that's even added after the fact. So we're going to do the transformations on those. That's what we're talking about when we're manipulating. We're going to do those transformations. So first of all, let's go back and review just a little bit. We know that if b is greater than 1, that's going to be growth. And what the graph is going to look like is as we go left to right, the graph is going to increase, like so. And you're going to have some key points on the parent graph. You're going to have the point 0, 1, and you're going to have the point 1b. So 0, 1 because anything to the 0 power is going to equal 1, and 1b because b raised to the first power is going to be itself. So that's why we end up with those. And what we're going to notice is that with this b greater than 1, that the limit as x approaches infinity of this p of x, if b is greater than 1, is going to approach infinity. So as we go left to right, this thing is going to grow and grow and grow and grow and grow and never stop growing. All right, so the other one that we would talk about was where b is between 0 and 1. And this is going to be decay. And decay just simply means that it's going to decrease in value over its entire interval. Now, very much the same here. We've got the point 0, 1. That's going to be on any of our base exponential graphs, regardless of whether it's growth or decay. So we've got 0, 1. And then over here, we're going to have 1 comma b. Now, you're probably wondering, well, why is it down here? Well, remember, in this case, b is between 0 and 1. That's why it can be lower than that one, where over here, b was greater than 1, so it's going to be greater than that point. It's going to be higher than that point right there. So in this case, when we talk about limits, the limit as x approaches infinity of p of x, in the case where b is between 0 and 1, is going to approach 0. Now, with both of these, it's really, really easy to find b. It's known as the ratio of consecutive terms. It does not matter which terms you use, as long as you use two that are consecutive, one after the other, and that is going to be found by something like p of n, where we plug in n, some n value, and we're dividing by p of n minus 1. So we're dividing by the term before it. and it doesn't matter what n is. N could be 2, and this one could be p of 1. This could be p of 10 million, and this would be p of the 9,999,999. As long as you do one term and the one before it. And that is how you can find b. Now, with these, you can have transformations. And in this case, transformations are going to reflect, shift, and dilate the graph. Now, remember, reflect is just where you're going to reflect that thing across one of a line, usually one of the axes, either the x or the y. Shift is just where we're moving that thing around. We're going to take key points and we're going to move them around. And dilate, that is where we're going to include the a, and maybe if we include something that is times the x up here in the power. And what that's going to do is that's going to stretch it vertically or horizontally, and also shrink it vertically or horizontally. So that's where we get those stretches and shrinks, is the dilations. Now, our overall function, base function, well, not really the base function, sorry. No, it'd be a base function, but it wouldn't be the parent function. Be the one where you can determine what all this stuff is, would be this. A times b to the x minus h plus k. Now notice that the plus k is not in the power. Let me write that smaller. All right, so exponent properties reveal the different transformations can leave the same effect, or can have the same effect. On that parent graph. And what that means is we've seen it before in x squared. We looked at it earlier in the year where when we start putting numbers out in front of that x squared, versus when we put them inside the x squared but multiply. Remember, inside is going to affect it side to side or horizontally, whereas outside the function multiplied times it is going to stretch it vertically or shrink it vertically. And we can get the exact same graph by stretching it vertically or shrinking it horizontally. That's what this means, that different transformations can have the same overall effect. In other words, you can do different transformations but get exactly the same graph. So there's not just one single way to get a certain graph. If you're doing it, you can do other things and get the same manipulation of the graph to get there. Now, the one thing that you need to be careful of, and it's coming directly from here, is that when you've got all this other stuff that's being done to it, that same rule does not work. F of n divided by f of n minus 1, that is not going to be b. So this is true once you start getting those transformations. It's great in the base graph, but when you start getting these changes, it's not always going to work because of what we're adding and subtracting and all that stuff. So be careful and not think that that's always going to have to hold true. There are possibilities where it can, but it's not a guaranteed thing. All right, so let's look at number 1 here. It says let g of x equal 2 to the x plus 1 plus 6. List the parent function and describe what transformations occurred to produce g of x. All right, so looking at this, the parent function is going to be 2 to the x. Now, what happened? Well, remember, inside the function is left and right. It's going to be opposite the way the sign tells you. So this is going to shift 1 unit left. And then the plus 6 is after the fact. So you evaluate this thing, and then you just add 6 to every y. So it's going to shift the whole function up 6 units. So shift up 6 units. All right, what is the domain of G and what is the range of G? Well, the domain of G, remember, is going to be the same thing as the domain of, you take the domain of 2 to the x and you see if the shift is going to make any changes to it. So if we look at the parent function, what values can I plug in for x? Can I plug in negatives? Yeah, I can plug in negatives. I'm going to get really, really small fractions. I can also plug in 0. 2 to the 0 would be 1. And I can also plug in all the positives. So just looking at what goes in and works, I know there's nothing that's going to make this thing undefined. There's nothing that's going to have a division by 0 error. And those are the basic 2 things that are going to cause domain issues. So our domain is going to be all reals. All right, so then you kind of need to look and think about the base graph of this. Well, let's think about the base graph of that. 2 to the x, my b value, 2, is greater than 1, so it's going to be a growth model, so it's going to do that. And what's the lowest value that I can get? Well, it's never actually going to get to 0, but it's going to get really close. So in this case, the range of the base, understand we're talking about the base right now. The range of the base is going to be y is greater than 0. It's never going to be 0. It's only going to be values greater than 0. And it's going to take off and grow and grow and grow over here. So that's why there's no limit on the top. All right, so that's the base graph. That's this parent graph right here. But what do we do with this graph? What do we do to the base graph to get this thing as far as the up and down, the range? Well, we shifted it up 6 units. So if this is the smallest value we can possibly approach on the base graph, and then we shift it up 6 units, well, now the range of this thing is going to be y is greater than 6. So you use that idea to find out where the base, the parent graph, is going to be, and then see what happens to the parent graph and see how it affects the domain and the range. So there is my domain, all reals, and there's my range. Y is going to be greater than 6 because I had the base graph had a domain, or sorry, a range that was greater than 0, and we shifted up 6 units. So that horizontal asymptote that we would have at 0 would actually move up to now positive 6. And we're going to see that when we sketch the graph down here in part D. All right, find the y-intercept of the graph of g. All right, so remember, to find the y-intercept, you're always going to let x equal 0. Always, always, always. To find the x-intercept, you let y equal 0. So to find one intercept, you're going to let the other variable equal 0. So we want this one because we want the y-intercept. So if we take this up here and we plug in x equals 0, we're going to have g of 0 is equal to 2 to the 0 plus 1 plus 6. Well, 0 plus 1 is 1. 2 to the first power is 1. Sorry, 2 to the first power is 2. And then 2 plus 6 gives us 8. So our y-intercept is 0, 8. All right, and then sketch the graph of g. Find the limit as x approaches negative infinity of g of x and the limit as x approaches infinity of g of x. All right, so here's the way I do this. You can do this differently if you want to. I want the base graph. I want those key values that I talked about in the notes. I'm going to put those in a lighter color, and then we're going to shift and see what happens to them. All right, so if we've got 2 to the x, so the parent is, whoop, so that means when I've got x equals 0, I'm going to have 1. So this is 0, 1. Now, guys, understand I'm talking about the base graph, the parent graph. It's not 2x, it's 2 to the x. And then when I go over 1, I'm going to be up 2. So that's the parent graph. Now, once again, go back and take those values and use that. I'm going to shift 1 unit left. So 1 unit left would go right there. And then 6 units up. So now I'm going to go 1, 2, well, yeah, 2, 3, 4, 5, 6. Actually, I need to go up one more, don't I? If I'm going up 6, I'm going to 7. That's not going to work real well, is it? Let me move these down a little bit. So 0, and we'll call that 1. And then we'll go over 1, and we'll go up 2. All right, so now let's take those and shift. So we're going to shift over 1, and we're going to go up 2, 3, 4, 5, 6, 7. I've got to go up 7, and I'm starting at 1. All right, and do the same thing with this one. I'm going to go over 1, and you're going to go up 6. So that's going to put you up at 0, 8. And 0, 8, we know, is one of our points on our graph. So now, if we were graphing the parent graph, we'd have this number right here. Something along that. Well, we've done the same thing, we've just shifted it. So that means we need to go up to 6, and we've got a horizontal asymptote at 6. Because remember, we've got a horizontal asymptote here at 0. Well, guess what? When we shift this graph, that horizontal asymptote shifts as well. So it's going to shift up to 6, and then now my graph is going to do that number. So there, in red, is f of x equals, I need to move that over, and that's g of x, not f of x. G of x equals 2 to the x minus 1 plus 6. Moved 1 unit to the left, that's a plus. And then 6 units up. So what's the limit as x approaches negative infinity of g of x? Well, as I go further and further in this direction to the left, this value is going to approach but never get to 6. because of that horizontal asymptote moving up. And if I do a limit as x approaches infinity of g of x, well, over here it grows and grows and grows, so it's going to go to infinity. All right, and if they say find this stuff, guys, when you're doing your work on these tests, quizzes, or whatever, don't just write the numbers. You've got to write out what it is and what it is, and if there's work to be involved to simplify anything, show that. You got to show it. All right, an exponential of the form f of x equals a to the x plus c is shown. Which of the following statements is not guaranteed? C is less than 0. Well, here's the thing. Remember, with a base exponential function, we would have a horizontal asymptote at x equals 0. My horizontal asymptote is now whatever this number right here is. And that indicates what? It indicates a vertical shift, but it indicates a vertical shift in the negative direction. So that means this value right here, to get to be a minus, would have to be negative. So that one is guaranteed. And remember, we're looking for what is not guaranteed. So that one is guaranteed. A plus C is going to be greater than 0. Let's come back to that one. All right, C. A, notice that A is, they changed the letter, but you still have to understand, even though this A is different from the A that we talked about yesterday or in 4.4, understand the location of it. Be careful. They're going to mix up these numbers, but they'll put them, or these letters, and they'll put them in different places. Understand what that part is. That is the base of the exponent, of the exponential expression. That's what you're worried about. That is the same thing that we had that was B in the notes. And what do we know about if this thing is going to be a decay? And this is a decay because it's decreasing. So it's an exponential decay. And for our exponential expression to be a decay, our B value had to be between 0 and 1. In this case, they just re-lettered it as an A. Don't get confused by that. All right, so that would have to be true. That would be guaranteed. And part D, the limit as x approaches infinity of f of x equals c. Well, remember, c is telling you what your shift was. We talked about the shift being negative in part A. And as we go off to the left, our function is going to approach that new horizontal asymptote value, whatever it is, and in this case it's C. So that one works as well. So now we go back up and look at B. A plus C is greater than 0. Well, do we have anything that tells us any kind of relationship between those two and what they need to be? No, there's not. So this one is the one that is not guaranteed. So their answer is B. All right, so this one goes back to that last little bit of information on the quick notes up there, where you can have two equations that give you the exact same graph. Well, let's be honest with everything. It's not going to be two different equations. They're just going to be generally in a little bit different shape. So we're looking at number 3 here. It says the equation for graph G in the card sort was y equals 2 to the x minus 1. And they want us to write an alternate equation for graph G that uses the vertical dilation instead of the horizontal shift and prove that the two equations are equivalent. All right, so y is equal to 2 to the x minus 1 power. Now, we talked about this the other day, and what we can do with powers, we can actually split this up into 2 to the x times 2 to the negative 1. Now, remember where that comes from, and if you don't remember, just pay attention, it'll make sense. So if we have x squared and we multiply that times x to the third, we end up with x to the 2 plus 3, which is x to the fifth. That's a long version of a rule that we've known for a long time, since probably before Algebra 1, that if you're multiplying the bases, you add the powers. Well, here's the thing. We're kind of adding the powers here, except remember, subtraction is nothing more than adding a negative. So that's why this is negative over here. And we're using the same property, we're just using it in reverse. So we were at this point right there, and then we went back to this point where we just split them up. Now, the reason we want to do that is because we're looking for a vertical dilation. We're looking for something outside of the function that's going to multiply it by something. And that's going to give us a dilation. Well, right now, there is our exponential expression. And we're multiplying it by this. Well, do you guys recognize what that is? 2 to the negative 1 is nothing more than 2 to the x times 1/2. Remember, if we've got a negative exponent, we can just flip it to the bottom and make it with the same exponent but positive. So we literally have 1 over 2 to the first power, which is just 1/2. So now we can rearrange this and put that 1/2 out front times 2 to the x. So remember, we talked about in 4.4 this being a times b to the x. So there's your vertical dilation, and the 1/2 is going to give you that. Instead of having a horizontal shift, you're going to have a vertical dilation that's going to give you the exact same graph. How do we know it's this exact same graph? Because it's the exact same equation. It's just in different forms. All right, so number 4 tells us to write an equation for an exponential function f that is increasing and concave down over its entire domain. So let's look at some of the ones that we've talked about so far. All right, so we've talked about our general b to the x. And remember, that one does that. So that is concave up. So it's not concave down, but it is increasing. So it's not going to be b to the x. All right, and then we've seen this is where b is greater than 1. So if b is less than 1, sorry. So if b is between 0 and 1, remember that's going to be a decay. And in that case, we're concave up, but we're decreasing. So we're not concave down in either one of these. So we know that one's not going to be it. What can we do? Well, we can flip them over. Remember, we've got reflections. We could throw a negative 1 out in front of our b to the x, with b being greater than 1. And what's that going to look like? Well, remember, if we throw a -1 out there times the b of x, it's just going to take every single b of x value, all these y values, and it's going to make them negative where they were positive before. So our graph is going to look like this. So now what do we notice? It's not increasing, but it is concave down. So we changed it over. This one was increasing, this one was decreasing, this one was concave up, this one was concave up. This one's concave down finally, but it's not increasing. So this one's not going to be it either. So then we just need to swap over here and analyze b being between 0 and 1. And if we look at that, remember all we're going to do once again is just flip this thing over. We're going to have something that looks like this. And that's a horrible graph. So now, looking at this, this is concave down. Remember, concave down means the slope is decreasing as you go left to right. And even that's not the greatest of graphs. There we go, that's a little better. So slope is decreasing, 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 approaching 0, but never actually gets there. And the function's increasing. So this is increasing also. So ding, 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 we have that. So what we're looking for is we're looking for a negative something times b to the x, where b is between 0 and 1. So you can write many different equations for this. So let's just say f of x is equal to, we'll say -3, and then remember our b has got to be between 0 and 1, so we'll use 1/2 x to the x power. That would work perfectly fine. You could also have something like -2/3 to the x, where the negative is outside. Guys, notice that the negative is not inside, it's outside in front. So -2/3 to the x. You can't put this. The negative is not part of your exponential base. The base of the exponent can only be positive. Now we can multiply it by negatives afterwards, but we can't take a negative base for an exponent. If our base of our exponent is negative, it's not an exponential expression. Those are mathematical expressions, but they're not exponential expressions. They're not going to be continuous. They're not going to be things that we can easily work with. All right, so like I said, yeah, that as long as you've got a negative out in front of it and some value between 0 and 1 in here for your base of your exponential raised to the x power, that's going to be okay. All right, hope that helped.